Today, we're diving into something huge. We're talking about the physics of a nuclear bomb, a topic with some seriously immense power and, profound consequences. We're going to break down the science, step by step, to really get a handle on what makes these things the most destructive force we've ever created.
So, it all boils down to this one, kind of mind-blowing question. How on earth can a man-made device unleash the same kind of energy that powers a star? That's the core mystery we're going to unravel together.
So, where do we even begin? Well, our story doesn't start with a weapon at all. It actually starts with a pretty revolutionary scientific idea, one that found a universe of potential locked away inside the tiniest of particles, the atom.
We've all seen it, right? Einstein's famous equation, E equals mc squared. But what's it really saying? Well, it's the bedrock for every single nuclear reaction. It tells us that mass isn't just stuff. It's actually a super condensed form of energy. And if you can figure out how to convert even a teeny tiny amount of mass, it pops back into existence as a truly staggering amount of energy. That's the secret key to everything.
And just how efficient is this energy release? Get this. In a nuclear blast, something like 99% of the energy from that converted mass is unleashed almost instantly. It becomes this devastating 1-2 punch of intense heat and a brutal shockwave. That's what causes most of the immediate destruction.
Okay, so how do you actually go about turning that mass into energy? Well, scientists found two main pathways. We're going to start with the first one they discovered, a process called nuclear fission. Basically, splitting atoms apart.
Now, fission doesn't work with just any old element. You need very specific types of fuel. We're talking heavy, really complex atoms like uranium-235 or plutonium-239. The key to these materials is that their centers, their nuclei, are just naturally unstable. You can think of them like a tightly wound spring, just waiting for a tiny poke to completely fly apart.
So, to set this off, 4 things have to happen in a blink. First, you use regular explosives to slam the fuel together, making it super dense, what they call a supercritical mass. Second, you fire in a single neutron to get the party started. Third, and this is the absolute key, that one neutron splits an atom, which releases energy and a couple more neutrons. Those new neutrons then go and split more atoms, which release even more neutrons, and on it goes. You get this out-of-control exponential chain reaction. And fourth, that runaway reaction unleashes that immense burst of energy all at once.
So that was path number 1. But there's a second path, and this one is way more powerful. Instead of splitting heavy atoms apart, this method smashes light atoms together. It's called nuclear fusion, and it's literally the same process that powers our sun. Now, this is a much trickier design, because it actually needs the first process to work. See, to get fusion going, you need temperatures and pressures that are just unbelievable. And the only way we know how to do that on Earth is to use a fission bomb as a trigger. So the radiation from that first fission blast floods a secondary chamber, instantly crushing and superheating hydrogen fuel, things like deuterium and tritium. This incredible force smashes those light atoms together to form helium, and in the process releases many times more energy than the fission bomb that started it all.
All right, let's just lay these out side by side. It makes the differences really clear. A fission bomb, or A-bomb, splits heavy atoms like uranium. A fusion bomb, an H-bomb, fuses light atoms like hydrogen. But look at the trigger mechanism. A fission bomb just needs regular explosives to kick things off. A fusion bomb, it needs an entire fission bomb just to get it started. And that difference in triggers is why the power isn't just a little bigger, it can be hundreds of times more destructive.
So, we've talked about how all this energy gets released. Now let's turn to the pretty devastating results of that release. What actually happens in the moments and days and years after a detonation? It really comes in a few distinct, destructive waves.
The very first and most immediate thing is the shock wave. This is basically a wall of air, compressed so tightly that it's moving faster than the speed of sound. It's just pure brute force, and it's what flattens buildings and obliterates anything in its path for miles.
Right along with it, traveling just as fast, is the second wave, heat. An absolutely blinding flash of thermal radiation that's hotter than the surface of the sun. It can literally vaporize things up close and cause massive fires and horrific burns even kilometers away from ground zero.
But even after the blast and the fire, the danger isn't over. That's when the silent, invisible threat arrives. Nuclear fallout. This is all the bomb's fuel and other materials that have been vaporized, made radioactive, and blasted up into the atmosphere. This radioactive dust can ride the winds for hundreds of miles before it settles back down, poisoning the land, the water, and the food chain for years, even decades.
And then there's one more effect, one that's especially scary in our modern world.
the EMP, or electromagnetic pulse. The detonation throws off this huge burst of gamma rays, which interacts with the atmosphere to create a massive electrical field. It's strong enough to fry unprotected electronics, knock out power grids, and basically cripple a modern society's entire infrastructure over a huge area.
The science here is just undeniably powerful, and its use as a weapon is, frankly, terrifying. But the story doesn't quite end there. The physics we've been talking about, it's a fundamental discovery about how our universe works. And like a lot of big discoveries, it's turned out to be a real double-edged sword.
And you can really see this deep conflict in how we treat nuclear science. On one hand, you have this weapon of war, so dangerous that its creation and spread are strictly controlled by international agreements like the Non-Proliferation Treaty. The whole goal is just control. But on the other hand, the very same scientific principles, controlled nuclear fission, are an incredible tool for peace. It's what gives us clean energy from nuclear power plants and what creates life-saving medical isotopes that doctors use every single day.
And that really leaves us with the ultimate question, doesn't it? We have unlocked one of the fundamental forces of the cosmos. The science is out there, the cat's out of the bag. The challenge that's left for us isn't a physics problem anymore. It's a question of our own wisdom and our own responsibility. The power is here. The real question is, can we as a species actually control how it gets used? Thanks for joining this Explain.